Okay, so you can see that when S1 and S2 are closed, that means the positive voltage is coming from this to this. Positive side is connected to load. Okay, so the output voltage is positive and current is also coming from this direction, so this is also positive. When D1 and D2 is on, that means D1 and D2 is on, means uh, the current is coming from this direction to this direction. So current is negative, but voltage is positive. But when S3 and S4 is closed, S3 S4 closed means the voltage and current both will be negative. Means it will come from this direction, from this to this way it will come. S3 S4. Okay, so negative to positive it is coming. So here both voltage and current will be negative. Okay, for S1 S2 closed, it was coming from negative positive to negative. So it was positive voltage current, and for S3 S4 closed, when negative to positive voltage is coming, so voltage current both are negative. Now when D3 and D4 is on, D3 D4 on means uh, D3 D4, for D4 on means this side will be negative side and this side will be positive. So negative and positive. And here also for D3 this will be positive this side and this will be negative. Okay. So the voltage is coming from negative to positive, so it will be negative, and the current direction is positive. Now the output current. What will be the output current? Output current for switch 1, switch 2 on. This will be the output current. This is the output current IO. Okay. And this value is VDC by R. R is the load resistance. This will be equal to VDC, the supply voltage, divided by resistor. Okay. Now, if I draw the voltage output, then also the output voltage is the positive and negative half cycle same, that is VDC. VDC output voltage we can obtain. This is output voltage. Okay. So this is only for our load. Clear? Now, when it is RL load or RLC load, the situation will be somewhat different. Different means what? Suppose this is a switch, uh, switching on and switching off. This is S1, S2. This is S2. Suppose this portion is S3, S4. Okay. This is S3, S4. And this is S1, S2. Okay. So now if I consider for RLC load, what will happen? Uh, if this to be the switching times, this to be the switching times, then what will happen? This is the portion, it will go on, and this way it will go. So what you can see that there is a residual portion, and this is known as, suppose this portion when D1 D2 is on during this portion. Okay, this is the portion when D1 D2 is on, and these are the portion when S1 S2 is on. These are the portion when S1 S2 is on, and these are the portion when D3 D4 is on. This is for RLC load. D3 D4 is on. Okay, and this portion is actually the S3 S4 on. S3 S4. Clear? So this is for RLC load. Now, when it is pure inductive load, then what will happen? When it is pure inductive, then if this is the switching period, suppose, then this will be the total thing. It is so. So at mid portion it will come. This way it will go. Okay. So what will happen? This portion is for D1 D2. Okay. This portion is for D1 D2, and this portion is for S1 S2. S1 S2 on. So now for this portion, this is the portion when D3 D4 is on. Okay, and this portion is where S3 S4 is on, and the system repeats like this. Okay, now if we can derive the RLC load current for RLC load when the XL is much greater than XC, then I naught when XL is greater than XC, I naught is equal to 0.9 VDC by Zn. That is the impedance into sine omega t minus phi. Okay, and this phi will be is equal to tan inverse of XL minus XC by R. Okay, for pure inductance, this phi will be 90 degree. That means XL, this tan inverse XL minus XC by R equal to 90 degree for pure inductance. And when XC is greater than XL. Then what will happen? This is the switching period. This is the switching period. So this is S1, S2 on, and here it is S3, S4 on. Again S1, S2 is on. So this is the repetitive cycle, and this way it will go. So this is when XC is higher, much higher than XL. Then what will happen? Then the cycle will be like this. Okay. This portion will come like this. So this is the D3, D4 portion. Okay. This portion will be D3, D4. And this portion is D1, D2 on. Okay. And definitely this is S1, S2. This is S1, S2. Here it is S3, S4. Okay. And the cycle repeats like this. Now this phase difference, okay, because of the capacitive portion, the phase difference is this. This phase difference is actually the phi. This is the phi. And that phi is equal to tan inverse XC minus XL. Since XC is greater, XC minus XL by R. Okay. And this is the best example of load commutation. Load commutation means using different amount of load, the circuit turn off can be obtained. Okay. Here is 3, is 4. So again, here D1, D2 on. Okay. So this is all about the single phase full bridge inverter.